Today, we want to continue looking at this framing device business and specifically area under a curve and above an interval. This is going to give us an insight into how we want to think about integration. All right. Here's how I like to think about integration. Integration is multiplication, but one of the factors is continuously variable. Integration is multiplication, but one of the factors is continuously variable. Two things that are mucking with our multiplication business right now. Variable, continuously variable. Two problems. Calling this multiplication. The reason that these form problems is that this is not how multiplication works. Multiplication is addition when everything is the same. That's why this is weird to think about it this way. Multiplication is addition when everything is constant. Multiplication is addition when everything is the same. So what we mean is that if I write 5 plus 5 plus 5, that's an addition problem, but all the terms are the same. So we summarize that with multiplication. So 5 plus 5 plus 5 is 3 times 5. Everything is the same, so we get to use multiplication. We look at 5 plus 5 plus 5, and we say, awesome, we get to use multiplication because those 5s are all the same. Then we get to this variable business. If our terms aren't all the same, we don't get to use multiplication. We got to stick with addition. Good old addition, always there for us. It's like the basis for all this stuff. Even just bringing up the fact that there are terms is what's going to cause is why continuously is going to be a problem. But if the terms are not all the same, are not constant, then we're stuck with addition. Uh, 4 plus 5 plus 6. We don't get to use a multiplication here because the terms aren't the same. We don't get to say this is 3 times anything. I know that the sum is 15. Wait. Yeah, the sum is 15, so we could call it 3 times 5, but that's not what we're looking at. It's not about the 15. That's the great misinterpretation of math class. It's like, oh, math class, it's easier to grade because you only have one answer. The answer is like the least important thing that anybody does in a math class. Getting to the answer, that's the least important part. Or just writing down the answer, that's the least important part. Thinking about how things work to arrive at the answer, that's what matters. So it's not important that the sum is 15. That's why I didn't write 15 for the first one. The point is that we have an addition problem. The terms are different, so we don't get to use multiplication. But there's an even bigger problem in the integration category, which is why we have to have this calculus class. Our factors are continuously variable. That makes things way worse. If things are continuously variable, there's no next term. There's nowhere to put the plus signs. How is this going to work? That's us being shocked because there's nowhere to put the plus, because there's no next term. If I pick a real number 1, what's the next real number? That's the next integer. Integers form a countable set, so 2 would be the next integer, but what's the next real number? If by your silence you mean there isn't one, then that is correct. The real numbers are form a continuum. There is no next in a continuum. Whatever you pick for the continuum, for the next thing in the continuum, there's going to be an infinite number in between what you picked and where we started. This is weird. We don't like this. This is why we fight things like 0.9 repeating being equal to 1. It is. There is no question. If you disagree, you are just wrong. 0.9 repeating is 1. So there's no terms. There's nowhere to put the plus. That gives us a problem. No, we don't. In a sequence, we just have a list. And if we have a list, then we can number all the things. We can count all the things. We have a continuum. It just flows from one to the other. There's no next term. There's no next real number. Let's visualize what's going on here. I'm going to draw each of these, and we're going to visualize. Oh, I'm drawing secret stuff, so you don't get this. I'm just kidding. I'm drawing secret symbols, trying to summon knowledge demons. I'm just kidding. I did need that one. So I want to find the area. I've got 3 units down here, length of 1, 2, 3. Nice constant. 5. Here, we get to use multiplication because the length is constant. Area is just 3 times 5. Multiplication is addition when everything is the same. I can find the area, the only multiplication that we need, the only application of multiplication we need. We get there, we get to use multiplication. We learned this in nth grade, where n equals the number of the grade you were in when you learned about area of rectangles. I probably should know what that is, being a math educator, but I don't. It's like something you learned when you were kids. I can't even identify kids by age. I can only identify kids by essentially movement type. Like the immobile ones, that's infant class. The ones that are not very good at moving, they fall over a lot, that's toddler, which is great because that's a perfect description of like how they move. And then there's like teenagers, which are like fully mobile and kind of surly. And then there's like children, which are like in between toddlers. So they have all their movement for the most part, but they're not quite surly enough to be teenagers. And then there's like adults. Those are the only categories I know about ages. People would be like, oh, I saw this kid that did a funny thing. How old was the kid? You're asking me? The hell. This might be why I probably shouldn't have kids. Explains the dogs. Dogs are so much easier. Like if I need to leave my 4-year-old alone for a couple of hours, it's fine. You do that with a human child, and people are like, oh, you left your 4-year-old alone for 3 hours? I gave him something to chew on. I don't know. We're gonna have to take your children away from you. I don't understand why I'm being punished by making my life more convenient. I'm just kidding. I don't have kids that were taken away from me. Yeah. Still working on it. You believe in yourself. Here, our length is variable, but constant in chunks, right? So I can calculate the area with a 3, and this is a 4, and this is a 5, because oh wait, no, it's 4, a 5, and a 6. I wasn't able to use multiplication on the whole thing because the length was variable. There's 3 different lengths. The length is variable. Didn't get to use multiplication, just use addition. But in this last one, if we have a length that is continuously variable, in this picture, the length, the height that we were using before, is continuously variable. There's no next height. There's nowhere to put the plus sign. So here's 0. If this is just 0, 1, 2, and 3, same as before. And if I name this with a function, to keep things simple, the length here is continuously variable. Our first length is whatever the height of the function is at 0. But there is no next length because it's continuously variable. And this is where the problem becomes an integration problem. Integration is multiplication, but one of our factors is continuously variable. How's everybody okay? The punctuation showed up early on that one. This is probably where the punctuation goes. This would be the end of the first stuff. I'm gonna have to edit out that part where I'm talking about not having children. I'm not going to edit out the part where I'm talking about not having children because that would require me to edit a video, and I don't think I'm going to do it. Of course not, because you're like, oh, dude, we saw all this back in Calc 2. And even at the end of Calc 1, why are you doing this again? Because I'm not sure that this was enough of a focus previously. And it's the same reason I make fun of all your algebra skills. Even if you got an A in an algebra class, nah, I just don't buy it. Because there is no algebra class that is a complete picture of algebra. I can tell because you all seem to be under the age of 50. And that's about how long it takes to acquire like algebra skills. You know what I mean? I know you might think you have algebra skills. You might even be good at arithmetic, but the better you are at arithmetic, the worse I'm going to guess your algebra skills are. But you don't really need to know stuff. You know what I mean? It's kind of a curse to be really good at arithmetic. It gets in the way of understanding because you don't have to know how things work. You just do stuff. You know what I mean? Is anybody here really good at arithmetic? I'm terrible at arithmetic. You can ask me simple things like, what's 7 times 13? Why are you asking me? Ask Siri. 91. See, in my mind, I was thinking, let's see, what did I say? 7 times 13? I can't even remember what I said. I was thinking it was 70-21. Because in my mind, I was like, oh, 70-21. But I might be off, so I wasn't confident, but I didn't say that out loud. I'm glad I was right. Although I might just be right on the whole thing. Let's talk about how we deal with this continuously thing, because I think y'all know. Because Riemann sums. Let's just switch pages. Let's deal with the continuously part of continuously variable. There's me guessing that I'm not going to go on with 30. That gives everybody points. Oh, good. It's the last page. But that's because you all don't know me. I'm an expert at packing 5 minutes of knowledge into a half an hour. I learned it in Dungeons and Dragons, which, as you know, is packing a half hour of fun into 4 hours. Let's deal with the continuously parts of continuously variable. Here's our great plan. We just ignore that. We drop back to the previous case. I'm in trouble with the writings today. Incidentally, dropping back to the previous case that we already know, this is what we always do in math. We look at our new problem and say, how is this new problem like an old problem? And we just make it an old problem. And that's what we're going to be doing here. There are 3 tricks in mathematics. Number 1, add 0. Number 2, multiply by 1. Number 3, change your variables. Change what the problem looks like. Kobayashi Maru this stuff. So we're going to drop back to the previous case. What that looks like here is we're going to assume that the curve is flat in small chunks. We're going to drop back to the previous case by assuming that the curve is flat in short bursts. Because if you look close enough at a continuous function, it is flat in short bursts. If we look at, say, a parabola, the positive half of the parabola, x squared, it looks all really steep. And if you go from 3 squared to 4 squared, there's like this big jump in value from 9 to 4 squared, 16. But if you look close enough, there's not a big jump in value from, say, 3 squared to 3.0001 squared. The closer you look, the flatter it looks. It's continuous. That's why we can look at these big flat plains and say, ah, look how flat the middle of America is. It's not, it's curved. We're just looking at it very closely. Sometimes I use the floor, but the floor is kind of flat. But if we look at what it's sitting on, it's going to be curved. It's just like flat enough. That's what we're doing. We're just looking very close, and we're going to assume that the curve is flat for a little while. Draw a picture of what we're talking about. I'm going to simplify my curve. I know I said we're going to look at short bursts, and these are gigantic bursts, but I need to draw in between. So what we do is we think of the area under this weird curve, not as area under a weird curve. We just go from PS5 graphics to Game Boy graphics. You just drop the resolution down and say, well, I can't have this much change. I'm going to flatten it out. We're going to make the curve flat in short bursts. Now I got the song in my head. Now there's some missing, but this is an approximation. Here we are, assuming that the function is flat in short bursts. Once we assume that the function is flat in short bursts, now it looks like the previous case. We get to use multiplication, and we have a place to put the plus signs. Now we've got terms. I got three areas. I could just say, here's the first area. It's a rectangle, plus the second area, plus the third area. There's some stuff that we're missing. There's these semi-triangular pieces up here that we're missing that are not part of our approximation. We can get more of that area by increasing the resolution, that is, using more rectangles. So improve the approximation with more rectangles. So now I have 6 of these rectangles, and we've cut away at some of the missing areas. So I'd have A1, A2, all the way up to A6. And we've chipped away at some of our overestimate and included it in our estimate. Yeah, this is like when we're using things like midpoint formula and the trapezoidal rule. In this case, I'm using a left endpoint approximation just with twice as many rectangles. So there's some more area that we are now including. How's everybody okay? We just found we just decided on a way to approximate, and we've decided how to improve the approximation. And this is a calculus class. More rectangles means a better approximation. So how many rectangles should we use? Infinitely many rectangles. Because the calculus answer is always the same. Whatever you're doing to improve your approximation, do that forever. This is where weird stuff happens. Here's where we run right into the central tension of calculus. Discrete versus continuous. Because I took this continuous function, I'm modeling it with this discrete flat bits. All we're doing is calculating area with length times width. I should use this times because dot actually is a different kind of multiplication. For the length, I'm evaluating the function at a particular point, or at some point xi. Once we put an index on it, I'm saying let's make a list of x values at which we will evaluate the function. Once we make that list of x values, we're taking that continuous function where there is no next value and just picking values so we can make a next value. Because I got f1 or f at x1, x2, x3, and x4. I'm making a list out of things. I'm taking my continuous and modeling it with the discrete. And then we're going to multiply by the width, which is some small change in x. Once we flatten out the top, we can calculate area as length times width because we're making rectangles. Then what we do is just add up all of them rectangles. Yeah. I write one reasonable looking sigma per semester, and then the rest become like weird backwards threes. So here we're adding up all those rectangles. I'm using n rectangles. We start out 1 into the n. And then calculus says use infinitely many rectangles. F at xi is us making a discrete set of heights rather than our continuous height or length. The delta x is the width. Here we are adding up the areas of the rectangles. Each of these is area. And calculus says use infinitely many rectangles. Now this is just dealing with a single variable problem. And you're like, oh, dude, this is multivariable calculus. What gives? This is the kind of thinking that we're going to apply to every integral that we run into for the rest of your life. This is always just how integral thinking works. We're going to take some kind of multiplication. One of the factors is going to be continuously variable. We're going to have to flatten that out So if, for example, instead of having a function of one variable, a one-dimensional curve in two-dimensional space, if we have a function of two variables, that will produce a two-dimensional surface in three-dimensional space. And instead of area under the curve and above an interval, we will have the volume under the surface and above a region. And we will do the same thing. If I want a volume under the surface and above a region, then for all the points in the region, I'm going to flatten out the surface and multiply by some little, oh, it's not going to be a delta x, it's a chunk of area. A delta x times a delta y, a delta a. Area multiplied by the height given by the function, add them all up, and then use an infinite number of things. In this case, rectangular solids. Same thing. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Have a good day. See you later. Yeah. So if this is negative 4 and negative 2, that's not even the 0 not even six. No. 4 and negative 2 is that negative 1. Yeah. So we don't want 1, so it's not going to be right in the middle. So how far over on this? What's your delta x, delta y? So how much of the change is speed? So 4 is 20, and negative 2 is 15. So we're 2/3 of the way through from 20 to 15. Yeah. So 20 to 5. Right. So we don't want to average. If we average it, that's always going to find stuff in the middle. Think about drawing a line from input 20 output 4 to input 15 output negative 2. What does that make? Think about that. So your delta x, your delta y, your delta x is from 20 to 15 to 5. That's the delta of 5. And you want 2/3 of that. So 4 to negative 2 is equal to 6. So you go to negative 6. Negative 6 multiplied by, let's figure out what that is. Yeah, but notice that I failed on the last part. We always went the wrong direction. Oh, wait, no. It gives you a value, or I mean, it gives
two for A with two for four. And it asks what the interpret like what happened. I didn't really know.
So, I mean, you graph do that? So you're doing the right thing. It's, you have two inputs, right?
Yeah.
And one of the ways that you figure out what's going on is by fixing one input, or seeing what everything looks like. What happens if I change, I get this graph like here, you get one, and then it kind of like switches up a little bit.
So viewing things with two, it would have been different.
Yeah, because it would be, so like A is equal, it's like, there's like one little bound, and then when A is equal to two, so it's like, well, here's one, and A is equal to two, it's a little bit taller. So you can start to imagine this like distributing up, distributing up. So we're building a hill. You're looking at a hill through slices.
Through slicing. So these are okay.
Have you seen a topographical map?
Yeah.
Topographical map is flat, but it gives you a sense of height by like drawing circles where everything is the same. Like everything here's where everything is 0 feet, here's where everything is 10 feet, and then from there, we can try to construct the space.
So I should agree. And also the next question after that, try to match that thinking. I should also be doing the trying to well.
Yeah, and then think about taking slices of the 3D thing. So one of the keys on the mapping problems is that if you see something that has like an x squared plus y squared, that makes it so like if x squared plus y squared equals some number, you know that makes it squared. So if you in your function does not have some variation of x squared plus y squared, then you're gonna be in. And then start looking at other things like plugging in 0, or just looking at the structure. If it's like e to the x squared plus y squared, what is an e to the something like that? And then think about that. That's going to be something.
Okay. I would just
not really. It's just about
to, like think about it. Yeah. Okay.
And what we're for the longer view, what we're trying to do is think that we can do and how we can slice it up in our mind. Because eventually, if things aren't going to be 3D, we're only going to be able to do that. If I give you a 4-dimensional cube, we can only see it. Yeah.